Question 9 of this exercise says in figure 6.63 that you see below, D is a point on side BC of a triangle ABC such that BD by CD is equal to AB by AC. So D is a point on BC such that BD by CD is equal to AB by AC. So this basically means that AD divides BC in the same ratio as AB is to AC. So we have to prove that AD is the bisector of angle BAC. So if you think carefully, this question is actually simply the converse of the angle bisector theorem. The angle bisector theorem says that any angle bisector divides the opposite side in the ratio of the sides containing the angle. Now this problem statement is the converse of that. In this problem statement, we are given that the two ratios are equal. The ratio in which BC is divided is the same as the ratio of the sides containing angle A, and we have to prove that AD is the bisector of angle BAC. So we have to prove in this case the converse of the angle bisector theorem. So I am going to show you two different ways to solve this problem. The first problem involves a construction similar to the one we did when we were proving the angle bisector theorem in an earlier question in this exercise, and the second proof is somewhat simpler, so I'll show you what that is when we come to that. So let me start with the first approach, in which we are going to do a construction on this figure. So to do that construction, I'm going to move this figure down here to make some space, and we are going to do a construction that's somewhat similar to what we did for the angle bisector theorem. So we are going to extend the side BA, okay, like this. And now, so in the angle bisector theorem problem, we drew a parallel from C to the side, to the segment DA. But in this case, what we are going to do is we are going to take a point E on this extended ray such that AE and AC are equal. So this is the construction that we're going to do in this case. So let me write this construction. So we are extending, so we have extended BA and we have taken a point E on the extended ray such that AE is equal to AC. And also let's join C and E. Alright, now we are given that BD by CD is equal to AB by AC. This is given to us. So BD by CD is equal to AB by AC. That's given to us. But because of a construction, we also have AC equal to AE. So what we can do is, in this equality that we are given, instead of AC, we can write AE. So that will give us BD by CD is equal to AB by AE. So instead of AC, I have written AE. Now I want you to observe the triangle BCE carefully. Okay, so triangle BCE, I am highlighting this triangle. And in this triangle, what does this equality mean? This equality that BD by CD is equal to AB by AE. So BD by CD equal to AB by AE. Well, if these two ratios are equal, this immediately tells us that this segment DA must be parallel to CE. And this is the converse of the basic proportionality theorem. When you have a segment that divides two sides in the same ratio, then that segment must be parallel to the third side. Okay, so from this equality, we can now conclude that in triangle BCE, DA must be parallel to CE. And this is because of the converse of the basic proportionality theorem. Now let's see what DA parallel to CE means for the various angles in the figures. So let's mark the various angles. So let's take this as angle 1 and let's take this as angle 2. Remember that our goal is to show that AD is the bisector of angle BAC. So we basically have to show that angle 1 is equal to angle 2. Okay, now let's take this here as angle 3 and let's take this as angle 4. So we have just proven that DA is parallel to CE. So what does this mean? Can you figure out the various relations now between the angles if DA is parallel to CE? Well, angle 1 must be equal to angle 4. This angle 1 must be equal to 4 because these are corresponding angles, and angle 2 must be equal to angle 3. Angle 2 here must be equal to angle 3 because these are alternate interior angles. But what can you say about angle 3 and angle 4? Well, angle 3 and angle 4 are equal because of our construction AE equal to AC. So if you have a triangle in which two sides are equal, then the angles opposite those sides will also be equal. So if AE is equal to AC, then angle 3 and angle 4 will be equal. So let's write this. Angle 3 is equal to angle 4, and this is because AE is equal to AC, and therefore we can now conclude that angle 1 is equal to angle 2 because angle 3 is angle 2 and angle 4 is angle 1, and angle 3 is equal to angle 4, so angle 1 will be equal to angle 2, and this proves that AD bisects angle BAC. AD is the angle bisector of angle BAC. So this is what we had to prove. So as an exercise, I think one very helpful exercise for you could be to compare this proof with the proof of the angle bisector theorem and see how this is the converse of that proof. Okay, so doing this comparison will really help you understand this proof better. Now I am going to show you a second proof of this same result. So in the second proof, let's again start with the original state of the figure that was given to us, and so we have to show that AD is the bisector of angle BAC. So let's assume that the actual bisector is a line AE. Okay, so from A, let's draw this line segment AE, and let's assume that this is the bisector of angle BAC, and then we will show that AE and AD are actually the same. So AD will become the angle bisector of angle BAC. So this is what we are going to do in our second approach. So as I said, we are going to assume that AE is the angle bisector of angle BAC. Okay, so this means, so now we can apply the angle bisector theorem for AE because we have assumed AE to be the angle bisector of angle A. So by the angle bisector theorem, we can say that AB by AC, the ratio of the sides containing the angle being bisected, will be equal to BE is this length, by CE. Okay, so let's write this. So we can, using the angle bisector theorem, we can say that AB by AC is equal to BE by CE. But we are also given that AB by AC is equal to BD by CD. Okay, so let's write this. We are given that AB by AC is equal to BD by CD. This is given. So what can you say from these two things? AB by AC is equal to BE by CE, and AB by AC is also equal to BD by CD. So this means that BE by CE must be equal to BD by CD. Alright, so basically D and E, they divide BC in the same ratio. BE by CE is the same as BD by CD. Now using this, let's prove that E and D will be exactly the same point. So let's add 1 on both sides of this equation. So we have BE by CE plus 1 equal to BD by CD plus 1. So let's take the LCM. So we will get BE plus CE by CE on the left side, and on the right side we have BD plus CD by CD. Alright, now what is BE plus CE? Look at the figure. BE plus CE is simply BC. And what is BD plus CD? BD plus CD is also equal to BC. So what we obtain now is BC by CE is equal to BC by CD. So we can cancel out the BC terms from both sides, and this will give us CE equal to CD. Now, when is this possible? How is this possible? CE equal to CD. This is only possible if AD is the same as AE. Otherwise, CE can't be equal to CD. So we can conclude now that AD is the same as AE, and we assume that AE is the angle bisector of angle BAC. So this means that AD is the same as AE, means that AD is the angle bisector. So AD bisects angle BAC. So this is the second approach you can use to show the same thing, that AD is the bisector of angle BAC. So the first approach required a construction similar to the one we used for the angle bisector theorem, and the second approach did not require a construction. The second approach depended on using the angle bisector theorem. So both approaches are correct. On an exam you can choose either approach. Personally, I prefer the first approach because the construction in that approach is interesting, but the second approach is as accurate as the first one. Okay, so this completes question number 9. To learn more about how QMath can help you crack school and board exams, explore QMath Leap, a live online classroom program run by highly experienced and committed teachers.